I still lose sleep over this fact. The faster you move, the slower time ticks for you. That is a direct quote from astrophysicist Neil deGrasse Tyson. And honestly, I kind of want you to lose sleep over it too. It's just such an awe-inspiring, universe-altering sentiment that completely shatters our everyday intuition. Your heartbeat, your aging, the literal ticking of a clock on your wall, absolutely none of it is fixed. So let's dive right into this explainer and uncover this seriously strange rule that nature follows: time dilation. We're going to explore how your speed through space and the actual strength of the gravity around you literally dictate how you age. I know, it sounds like straight up science fiction, but it's pure mathematical, physical reality. Because this topic radically challenges human intuition, here's your quick roadmap. We'll start with the illusion of time, see how speed slows down time, and how gravity warps space-time. Then we'll hit the twin paradox, find the proof sitting in your pocket, and finish up at the timeless universe. All right, section 1, the illusion of time. Newton versus Einstein. To truly grasp this, we have to completely break how you currently perceive a clock ticking. For literally centuries, thanks to Isaac Newton, we all believed in this idea of a universal clock. We thought, 1 second here on Earth was exactly equal to 1 second anywhere else in the universe, for everyone, all the time. But Albert Einstein brilliantly proved that this is completely wrong. Einstein showed us that time is relative. It's an actual physical dimension. Space and time aren't separate things, they're woven together into this single, malleable, four-dimensional fabric that we call spacetime. And your personal experience of time? It depends entirely on your speed and the gravity you're experiencing. Moving to section 2. Speed slows down time, which is special relativity. Let's see how moving fast literally robs you of your time. This concept beautifully illustrates one of the most elegant ideas in all of physics. Everything in the universe is constantly moving through space-time at the exact same total speed, which is the speed of light. Because that total speed is constant, it works kind of like a cosmic trade-off. If you're sitting completely stationary right now, all of your motion is moving through time. But the moment you start speeding up through space, you actually have to trade away some of your motion through time. So as your speed through space increases, your flow through time simply has to decrease. Now, to make this whole crazy system work mathematically, the universe relies on something called the Lorentz factor. Basically, this is the exact multiplier that dictates how space and time stretch and contract to make absolutely sure the speed of light remains a constant for every single observer, no matter how fast they're going. If time has to stretch to guarantee light always measures at roughly 300,000 kilometers per second, the universe will stretch it. So the catch here is that at everyday speeds, driving a car, flying in an airplane, the Lorentz factor is so incredibly small you'd never even notice it. But check out this data. Once you start moving at 10% the speed of light, your time runs at 99.5% normal. Hit 50% light speed and time drops to 86.6%. And get this, if you somehow manage to build a rocket that travels at 86.6% the speed of light, your clock, and I mean your actual biological aging, ticks at exactly half the normal rate of someone just standing still on Earth. Okay, section 3, gravity warps space-time or general relativity. What's really wild here is that you don't even need to move to experience time dilation. The deeper you are in a gravitational field, the slower your time flows. Because gravity is actually slightly weaker the further you get from the center of the Earth, a clock up on the high summit of the Himalayas physically ticks faster than a perfectly synchronized clock left all the way down at sea level. You are literally aging slightly faster standing on a mountain than you are down in a valley. Picture mass like a heavy bowling ball sitting in the middle of a trampoline. The Earth curves the actual fabric of space-time downward. And that deep curve doesn't just pull objects in, which is what we experience as gravity. It literally slows down the passing of time within that curve. The stronger the gravity, the more extreme the curve, and the slower time ticks. Section 4, the twin paradox. Let's look at a step-by-step story to really anchor all this theory and see just how dramatic these effects can get. Imagine identical 32-year-old twins, Anjali and Rohan. Anjali stays safely here on Earth. Rohan, however, boards a futuristic spacecraft capable of traveling at 86.6% the speed of light. He takes a 5-year outbound trip to a distant star, turns the ship around, and takes a 5-year trip right back to Earth. Now hold on, you might be thinking, well, since motion is a relative, from Rohan's perspective on the ship, isn't the Earth the thing moving away from him? Why isn't Anjali the one who ages less? The secret is in the turnaround.
To come home, Rohan has to fire his engines, endure this massive deceleration, physically turn around, and accelerate back. He actually feels that change in inertia. Anjali never accelerates. She just stays in one single frame of reference. That acceleration completely breaks the symmetry. Rohan is unambiguously the traveler here.
So, when Rohan finally lands and they reunite, the results are just staggering. For Anjali, 10 years have passed. She's now 42 years old. But because Rohan was moving at 86.6% light speed, where time runs at exactly half the rate, remember, only 5 years have passed for him. He's just 37 years old. And this is an irreversible physical reality. It's not some optical illusion or a broken clock. His cells, his heartbeat, his actual biological age is literally 5 years younger than his twin sister. Section 5. Proof in your pocket. You might be sitting there thinking this only applies to astronauts and thought experiments, but the proof of relativity is in the real world right now. 11.6 kilometers per day. That is exactly how much the navigation map on your smartphone would fail by. Every single day, if it didn't account for Einstein's theories of relativity. Within just a few hours, your GPS would be totally, completely useless. Let me explain why. Your GPS relies on satellites orbiting about 20,200 kilometers above the Earth. Because they're high up where gravity is a lot weaker, their clocks naturally tick faster than ours by about 45.9 microseconds a day. But because they're also zooming around the Earth at nearly 14,000 kilometers per hour, velocity time dilation slows their clocks down by 7.2 microseconds a day. Engineers literally have to combine those two opposing effects, applying a net correction of 38.7 microseconds daily to the satellite clocks before they even launch, just to keep our maps working. Einstein's theory is pure everyday engineering reality. On top of that, nature runs its own tests 24/7. When cosmic rays hit our upper atmosphere, they create these unstable particles called muons. At rest, a muon decays in just 2.2 microseconds. Even moving at nearly the speed of light, they should theoretically only travel about 660 meters before decaying into nothing. And yet, detectors on the ground pick them up all the time after a 15-kilometer drop. Why? Because they are traveling at 99% the speed of light. Their internal clocks slow down by a massive factor of 7. Time literally stretches for them, allowing them to easily survive that long trip to Earth's surface. Let's wrap up with Section 6, the timeless universe. We're going to push this to the ultimate extreme. We know for sure that the faster you go through space, the slower you go through time. So what actually happens when you push that to the ultimate maximum? What happens to time when you reach the absolute speed limit of the universe, the speed of light itself? What entity out there experiences literally zero time? The answer is light itself. Because photons travel at exactly the speed of light, that Lorentz factor we talked about becomes infinite. From a photon's perspective, no time passes at all. A photon emitted from a distant star 30,000 years ago that just happens to hit your telescope tonight has experienced absolutely zero passage of time. To that photon, the moment of its birth and the moment of its absorption happen in the exact same instantaneous second. For light, the universe has no duration. And that brings us to the profound truth at the heart of this explainer. Time is not this universal river flowing equally for everyone. There is no absolute now. Every single object, every person, every planet, and every tiny particle in the cosmos follows its own unique world line through spacetime, carrying its own deeply personal, perfectly valid clock. Time does not pass equally for everyone. Nature never promised that it would. Einstein didn't just change physics. He fundamentally rewired our understanding of reality. So the next time you look up at the night sky, or honestly, even just check the map on your phone, remember that time is quite literally what you make of it. The faster you move, the deeper into gravity you fall, the more your timeline diverges from mine. So I'll leave you with this thought. Knowing that your speed dictates your time, what path through space-time will you choose?